Hello and welcome to part 2 of the introduction talk to lab number 9, Analog Electronics and Physics. Now, last time you should have, ideally, produced a set of 6 results, one of which would have looked something like this. The blue theoretical line going through all of the red measured points, and the poles and zeros and gain that set the theoretical line through the measured points should have agreed with your theoretical predictions of what each of those networks should do. For example, this one, we have a pole at 115 Hz, we have a zero at 0 Hz, and we have a gain of minus 41.3 dB. And that corresponds to a circuit which looks something like this. If I let this be C and R, then the theoretical analysis of this would be, well, standard way of doing it. We replace every passive component with its complex impedance, which for a resistor is just equal to R, and for a capacitor is equal to 1 over j omega c. And then use the potential divider formula to tell me that the response of this, which is V out over V in, remember these are both phasors for this, is, in this case, R over R plus 1 over j omega c, and I can get that in the form of the ratio of two polynomials by multiplying every term, top and bottom, by j omega c. That gives me this. And from that, you can see that there is one zero, one value of j omega for which the numerator is equal to 0, and that is when j omega is equal to 0. So that gives me a 0 at 0 Hz. There is one pole, and the pole occurs when the denominator is equal to 0, and for the denominator to equal to 0, j omega rc must be equal to minus 1, so j omega is minus 1 over RC. The break frequency of that pole, which is what is plotted in the diagram here. Yeah, the software does say pole 115 Hertz. It should really say minus 115 Hertz. That's the break frequency of the pole, rather than the pole frequency itself. But that gives me a break frequency of this pole at 1 over RC. And remember, that's in radians per second. The program works in Hertz. So in Hertz, the pole's break frequency would be 1 over 2 pi RC. And the experiment says that for my circuit, that is at 115 Hertz. Does that work for my particular network values of resistor and capacitor? Well, hopefully it does. The value of the gain in the program is the gain at 1 Hertz. That's not so important. It's not that easy to derive from the form of the frequency response, so I wouldn't worry about that too much. The important thing is to get the poles and the zeros in the right place and the theory agreeing with the experiments. Now, scope probes. Another part of this lab is to look at how times 10 scope probes work. Well, a times 10 scope probe wants to give the output at this point here 1/10 of the input here for all frequencies. And I have to get this network here chosen so that this output here is 1/10 of this, no matter what the frequency is. What then does this resistor have to be, and what does that capacitor have to be? That is the puzzle to work out. I think it then asks you to have a go at building either a times 2 or a times 5 scope probe and see if that works. The final part of this lab is then to look at step responses. Now, the step response is the output of a circuit when the input to the circuit is a unit step. A unit step is a waveform which is 0 for all negative times, and then jumps up to 1 at time t equals 0, and remains at 1 for all positive times. Well, clearly it's not possible to produce a true unit step in the lab. It would have taken an infinite amount of time to do that, but what we can do is produce a very slow square wave. And the function generator can produce very slow square waves. Now, provided the square wave is 0 for long enough, and by long enough I mean plenty of time for all capacitors to discharge fully, and it is high at 1 volt for long enough, and again by long enough I mean plenty of time for any capacitors in the circuit to charge up fully, then we will get a very good approximation to the step response just by looking at the oscilloscope just after a rising edge has arrived from the function generator. So that's what we do. We produce a very slow square wave, maybe something like 1 Hertz square wave coming out of the function generator, and then we zoom up on the scope so we're only looking at the time just before and after the rising edge of that square wave. And in some cases we should see a step response that looks something like this, as shown in the diagram here. We haven't done the theory of step responses yet. We will be doing it soon, but for now, just record what happens. Then we'll try and compare that with theory and explain it in the lectures coming up soon. Right. For those of you who would like a challenge, you should have found that none of the 6 circuits that we've been investigating in this lab produce any gain, in the sense that in no case is the output amplitude bigger than the input amplitude. The puzzle is it possible to build a circuit composed of just capacitors and resistors, so-called RC circuit, for which the output amplitude is bigger than the input amplitude? If so, how do you do it? And if not, can you prove that it's not possible to get an output amplitude bigger than the input amplitude? It's not an easy challenge, but I think it's a very interesting one. So if anybody would like to have a go, good luck. I'd be happy to discuss the results with you. Okay, that's the end of this one. Good luck.